Test 1, 2, 3. Good, thank you very much. Maybe I should have a quiz today and give you like 10% for those who are here. It will be simple. Write your name. Okay. Okay. Good morning, everyone. So before we start the new material, just want to go through the quiz, the exam. Sorry, the exam again. So it will be during the lecture time on this Wednesday. It's still 1 hour and 15-minute exam, but you can really log in 15 minutes earlier, or you can stay 15 minutes after. So any question about the time for the exam? That's for the advanced students. Any question about the exam? Logistics. It will be on Canvas. Just click on the quiz. Yes. 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 So that's the problem. Partial credit might be an issue, but I'm trying to put too many sub problems so you don't lose partial credit. So. Yes. No, you will be solving stuff, but I don't need to see it. So you look at the final output, or I'm trying to put too many sub problems so you can really get some partial credit. Okay, so you should see some problems. They have quite a bit. Please, you will have like maybe 10, 11 sub problems. So what? Good ones. It doesn't mean how many problems, because some of them they have like 5, 6 sub problems, 10 sub problems, right? So okay, I posted this. These are the instructions on Piazza last night. I'm not sure if you had the time to look through these, so I just want to give you a couple of minutes to read through them and ask me any question about these instructions. About the problem, I mean, okay, about the exam problems. So, like, for example, you can ask clarity problems, like what do you mean by this in this problem, like in this question, and I can answer that. But if you start to say, I'm plugging in this matrix or this numbers in my code doesn't work, that's you are revealing, you know, the question. In that case, just send me a private message, or to Salim, but I will be online that time, and then we will have a live Q&A in Piazza, so you can ask your questions there during the time between 9 and 11. Any question about these instructions? Okay. So don't rely on searching on Google. I think that might be an issue that will waste your time. The exam is very tight. I mean, 1 hour, 15 minutes is 1 hour, 15 minutes. So, but I would rely on your code from the homework problems. Have it ready there. Just know exactly which problem you want to go to use certain code. That will save you time. Not, you don't have to use the code. You can really do calculator or MATLAB or Excel. But I think using the code that you already built is the easiest to do calculations. Okay. So we finished classification, where basically we yes, question. It's very, very tight. Okay, I will look into it. Okay. I have to ask Salim. Salim is really kind of managing all the homeworks. I want to see his grading, if he's okay with it or not. Because I know he's traveling this Friday for something. So, okay. So classification, as the name basically implies, we are really having a certain number of classes, and then we are to kind of pick for a certain input which class it belongs to, right? And then we have regression, where we do prediction. Like we have a quantification, basically, where this is fitting a line, fitting a curve, or fitting a function, right? And now we move to clustering. So this is the third chapter in our material, where we have certain data. I'd like to really kind of put them into cluster. And you can see that means we are really assuming there is an underlying similarity and dissimilarity, right? So there is a data point that's really similar to another data point, but also dissimilar to other data points. So that's really what clustering is. And it's really very important to always keep in mind what each one of these applications means. So today we'll just have the introduction to clustering, what kind of different similarity and dissimilarity distances we are talking about. And then we look at the simplest and the most well-known k-means clustering. Okay. So if you remember in the first week, we talked about supervised learning and unsupervised learning, right? Do you remember what the difference between them? So supervised learning, basically you have labels, right? So the training data, not only you have the X, but also you have the Y. So you have the labels. Either you have classification or you have regression, you still have the labels, or segmentation even, you still have the labels for the data. So you have the ground truth to start with. In the unsupervised learning, you have the data, but you don't have any labels. You don't have any ground truth that really guide your learning process. So clustering is really one of those where it's an unsupervised learning. So by definition, you have certain number of data, and now you start to build knowledge about how you would like to really kind of put these data points into clusters based on some metric, based on some measure, based on some similarity or dissimilarity measures that you have in mind. Of course, you need to use any side information you have about the data. Like if you have a physical phenomenon that's really caused the data, you have some assumption of the data, that will be very, very helpful in guiding your clustering algorithm in here. But in general, is an unsupervised algorithm, and that basically makes it more difficult than what we have experienced with classification and regression. Also, it makes it more ad hoc. So now you cluster, but you don't really have the ground truth, right? So now you start to say, okay, how well I am doing, right? So that's basically another. I don't know if it's a pros or cons, but it's really kind of you have kind of misguidance or lack of guidance in the process in the clustering. So now we'll look at the applications. Really, kind of tons of different applications. In homework 4, you will do this problem. The last problem, it will be an open-ended problem where I give you images like this one, for example, the one on the left-hand side in here, each one of them. And then I ask you basically to cluster these into, the easiest will be what? Background and foreground, right? So this is really clustering. Basically, you look at the pixel to say the pixels that really belong to the animals in the foreground, they belong to the same cluster. Any other pixel in the background belong to another cluster, right? But it really gets very, 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 very tricky, right? If you look in here, for example, you look at this one, if you just use the color, this will be a problem, right? So this one will belong to the animal, but it's not really part of the animal, and so on. So you can see that there is quite a bit of variations. In here, you can see the different colors, meaning we have different clusters. So we have even more clusters. So this will be the last problem in homework number 4, where you need to use clustering to do segmentation, right? So segmentation is very, very tough. What is segmentation and classification? Anybody knows the relationship between segmentation and classification? Yes. What does it mean? You elaborate. I mean, so you can think of it as basically each cluster is a class, right? But what are you doing differently in here? So what did we do? Yes. Exactly. So now in the classification, all what we did so far, you have a whole data point, either a whole vector, you have a whole speech, basically wave, you have financial data vector, or you have the whole image, and you classify the whole thing. Now in segmentation, we are really classifying every single pixel. We are saying to this pixel, does it belong to cluster 1, 2, 3, or 4, or class 1, 2, 3, and 4. So we're doing clustering is nothing but really segmentation is nothing but classification at the pixel level, right? And that's what makes it really, really tough, very, very difficult, right? Because we don't really have perfect data, right? So for such images, right, because you have some context in here, you have color, you have picture, it becomes easy. But for those, like Rahul is one of them, using something like seismic data or MRI or X-ray, right? You don't have color, you don't have that So and it's very noisy data. So segmentation becomes extremely difficult, right? Although it's one of the major application in segmentation is medical data, but it's very, very tough. So you'll do one of these practices in homework 4. Same thing for gene expression data. Again, another clustering challenge. And I just want to go through the list of them. You have news articles, how you can cluster them, and I will show you just an example in a minute. Different languages, some different hierarchy, linguistics, and so on. Species, and these are kind of a list of all different applications, and the list really goes on. Quite a bit of applications for clustering. Okay, so we did this on ChatGPT. One of my students, Ahmed, he did this where he asked ChatGPT, basically gave him like 4 different codes. 2 of them you can think of them as wisdom, although I don't totally agree. And then 2 of them belong to the news articles, right, as the news pieces. And then just ask ChatGPT to cluster these into 2 clusters. So really cluster in group 1 the wisdom phrases, and then group 2 basically the news articles, right, the news headlines, right. And now the more interesting part is this: when he asked ChatGPT, how come did you cluster in this way? I will just make you read the answer in here. Right. So basically, it just identified that basically there is a metric, and that basically metric in here is really has to do about philosophical versus factual content. Right. So we have that's the measure. That's the basically what ChatGPT really based its decision on. So this is really our criteria in this example in here for what we mean by similarity, right? Now for this data, because this data is really is a category data, means that we don't really have quantification for it numerically, right? So now the similarity has to do something to do with something of this sort, right? But in our examples in homework 4, we all deal with something that we can really measure mathematically. Let's look at this example in here. So we have 15 samples, and we use these samples in a classification, by the way. So we have these 15 samples, and now for each sample we have 2 features. You can see there are 2 features, xi1 and xi2. We can plot these onto the feature plane. So we have xi1 on the x-axis, we have xi2 on the y-axis, and this is our data, and this is our matrix X for our input data. And now basically we say, let's really kind of cluster these, and you can say, okay, now we can really do it by hand by looking basically at where the location of these into the feature space. So we can cluster these into 3 features, 3 clusters. So this is cluster 1, cluster 2, and the cluster 3. And this is basically the color labels corresponding to those. And now in doing so, what did we do? Basically we said, okay, these are very close to each other in this feature space. So most likely, basically, they belong to the same cluster. Same thing in here. These are very close to each other, so they most likely they belong to the same cluster, and so on here. So among these clusters, you can imagine that basically we have to question ourselves about this one. Does it really belong to this one's in here or that one? So in doing so, if I want this one, because it's very clearly basically these 2 points in here, this one and this one belong to the same cluster. If I want to make this closer to that one, but this one here is much farther away from these 2 than it is to these 2, right? So now that's a decision I have to make. And you can see this in the algorithms later on when we talk about clustering. That has to be taken into account. Right? Now, if we increase the number of clusters, then maybe I will have much more freedom in assigning this one to be different than belong to this cluster. Maybe this one is on cluster. Maybe these 4 will be the own cluster, and this one is own cluster, right? That could be. So the number of clusters can vary quite a bit your clustering, right? And there is really no kind of a systematic way how you choose your cluster number of clusters, right? It's another hyperparameter, and you will see basically the recommendation that mostly work. You try it for different k, and then see which one give you the best results or the more stable results. But that's kind of just to get you kind of a feel of what clustering and so now proximity measure is extremely important. So now if we look at what we just did in the proximity measure that we in this example, then all what we applied is just L2 norm, right? We just applied L2 norm in the two-dimensional space, basically how far they are from each other, including distance-wise, right? So now when we are doing clustering, now what I did in here, obviously we did what we call crisp clustering or hard clustering, meaning that every single data point, it will have only one cluster, right? So it has only a membership that just the size of the membership vector is only one, right? So it can only belong to one cluster. It does not belong to any other cluster, right? However, as we saw in classification, remember when we had the logits at the very output, basically when we have a probability vector, right? So we have maybe the class 1 is 80%, class 2 is 15%, the class 3 is let's say 5%, right? We have a same thing in here. We could really have design a cluster algorithm where we have soft clustering, meaning that we have a membership vector that really the length of it is the number of clusters that we have. So for each data point, I have membership vector, and then the first number will tell me basically how much membership does this data point have to cluster number 1. The second number, how much membership it has into cluster 2, and so on. That's basically a membership cluster, and that actually becomes more interesting because, like, if you ask me about this one here, for example, again to this example, I would say basically it makes more sense to use soft clustering because maybe it belongs to this cluster here to some, let's say maybe 80%, but 20% to this cluster as well, right? And still, it's very obvious, it's very far from this, right? But that will be much more robust than having just a hard clustering where basically the membership vector is only one in this case. Okay, so now just to formalize what we are really talking about mathematically, we have again our n samples as before, right? And each sample has p features. So we have this vector of dimension p or length capital P, and then we are really looking at that we have to assign each data point to a cluster. If you take the union of all our clusters after we finish clustering, then you get the data back. So we have really capital X back in this case is the union. Any cluster, it should not really be an empty set, right? Any cluster should have at least one data point, right? And that's, for example, if you say, okay, I would like to start with 10 clusters, right? And then 2 of them have no data points. That means K should be 8, right? And then you repeat it again for 8 and so on. So that's one. And now for hard clustering, the intersection between 2 clusters is equal to the empty set, right? There is no overlap, right? That's only for hard clustering, not for soft clustering. No. Okay, and basically this is what we have in here. So cluster 1, 2, and 3. And you can see basically in here, if you take the union of all of the clusters, you get your data back. None of the clusters is an empty set, and the intersection between the clusters is also an empty set in this case. Okay, so one very important method or measures to use is the L2 norm, including distance, but also we have some other similarity measures. And cosine similarity is one thing that we will study today, but also we'll get back to this after we finish CNN because it has really very, very important. And I just want to give you a hint of it. When you look at the gradients, like when you do the back propagation and you have your gradients, to compare how the gradients really move or how your manifold move from one place to another. Including distance, it just gives you the distance, how far they are from each other, right? The cosine similarity give you the orientation, right? Give you basically how not only how far the manifold moved, but also in what direction it changed. And that's actually, I will show you later on, maybe the second half of March, about how that can be very, very effective to compare different neural networks with each other. And then we look at basically Manhattan and other distances today. Okay. So now, as we talk about proximity measures, then we are really talking about similarity function and dissimilarity function. And that's very, very important. It gets a little bit confusing because like the k-means and other methods, sometimes they rely on similarity, sometimes they rely on dissimilarity. So just keep that in mind when, because it can get a little bit confusing because it's really the inverse of each other, and at least at the very basic logic of things. Okay, so cosine similarity, as you can basically imagine here, we have feature 1, we have feature 2, we have xj and we have xk in here. Then we can imagine that basically we have the inner product of that. What is the inner product of these two vectors? Is nothing but basically the magnitude of the first one times the magnitude of the second one times the angle between them, the cosine of the angle between them, right? So that's basically the inner product, right? So the inner product between two vectors, right, is basically the magnitude of the first one, the second one multiplied by the cosine of the angle between them. That will give you the inner product. So basically, we can really use cosine theta as the inner product scaled by the individual magnitudes of each one of these two vectors. That will give us basically the similarity. So cosine here is really similarity, right? So now, if you look at it's, I'm saying here independent of the magnitude, and I want to clarify what that means. If basically they are really identical, that means if theta is equal to a 0, what is cosine 0? Is 1, right? So they are really identical, right? So now, if the angle between them is 0, this will become a 1, right? That is the case. It doesn't matter what the magnitudes are, right? That's orientation, right? It doesn't matter what this. So basically, it doesn't matter what the magnitudes are. We will always have basically cosine of 0 equal to a 1 in this case because they are equal. Go to the other extreme, basically, where we have pi over 2, right? If I have cosine pi over 2, like in here, that means they are orthogonal to each other, right? So the basically that will be what? The value will be equal to a 0, right? That will be a value equal to a 0. Now, if you take to the all the way when I have them in opposite direction, right? So you have what? You have a -1, right? So now you can look at the scale. The scale of our cosine similarity measure is between -1 to 1, where -1 is the least similar, 1 is the most similar. And at these extreme cases, the magnitudes will not make a difference, right? In that cases, right? And then in between, we have this pi over 2, where the cosine of pi over 2 equal to a 0. Then in that case, they are orthogonal to each other. That means what? They are not correlated to each other. They don't have an impact on each other. They are uncorrelated, right? So now you have the scale from the least similar, the maximum similar, and in between we have the uncorrelated features in between these two. Now, if we want to use this, and again, I am using S in here, I'm going to remind you again of this. Similarities in S, this similarity is a D, right? Or distance, how far, right? So cosine is a similarity. That's why we call cosine similarity. If when I use a distance, then I just have 1 minus cosine of theta, right? In that case, my D will be between 0 and 2, right? You see that? That's because 1 minus 1, that will be a 0. 1 minus -1, that will be a 2, right? So it will be between 0 and 2. Any question about cosine similarity? Okay. So it's all about orientation. So now, yes. Okay, so in our proximity measures, like the title of the slide, right? We are looking at, usually we like to look at the distance, right? How far they are from each other, or how dissimilar they are from each other, right? Cosine similarity is as a measure, is about how much they are similar. So now to use that as a distance, then you have to have 1 minus that, right? So basically, this is the relationship between similarity and dissimilarity, right? So although maybe it's not extremely accurate, but I'm just equating dissimilarity as distance for now, okay? And that's basically cosine similarity is really a similarity measure, how similar they are to each other, because I can tell that from the numbers in here. And of course, I mean, if the closer I am to 1, that means I'm still similar, right? The closer I am to -1, it means dissimilar. The closer to 0, that means I am uncorrelated to each other. And I'm using that as a distance. And yes. Yeah, that's the easiest way to look at basically from a 2-dimensional space, or even a 3-dimensional, you have 2 hyperplanes, how the angle between them, right? But you go to n-dimension, it's the same thing. That's when we talk about the gradient later on, they are really in-dimensional space. And now how they are close to each other, how much change is happening in the gradients from one step to the next step, right? And not only magnitude-wise, right? Because still magnitude is very important, but also orientation, right, is very important. Yes. So in the extreme cases, if I have this one as like, for example, in here, like if I have this is 0, theta is 0, right? It doesn't matter what this magnitude is, right? Yeah, that's, it doesn't matter in this case. Yes, exactly. So that's what I'm talking about. Is the theta is 0, so cosine of 0 is equal to 1. It doesn't matter what the magnitudes are, right? So that's basically what, that's why when we use this for the gradients, then we have both of them. We have the cosine similarity, but also we have the magnitude as well as another way to look at it. Because we will talk more about it later on. Okay, I will talk about the gradients. Okay, so here's an example. I have two data vectors. This is x1. I don't know what's the dimension of the p in this case as 10. And then I have the second data sample x2, and then is 10 features in here. Take the magnitude of the first one, then we get this number. The second number data, we get this number. The inner product is this, and then take the inverse of the cosine, then you will get 0.68. So now you have 0.685 as our dissimilar. The similarity is 0.315, so it's closer to the zero in here, right? When you have something like more sparse in this case, then basically we have a much more efficient computationally calculate the cosine similarity. And again, if we have more than one data point with two features, then what usually we do, and this in clustering is very common. You'll do this in the homework number 4, where we create this similarity table, right? So this is what we refer to as pairwise similarity. So basically, you have your data point on the column, in one in each column, and then also you have it on the rows. So you can imagine basically if I have the cosine similarity, then the diagonal in here will be equal to 1, right? Because I'm comparing x1 to x1, that should be 1. They're identical. x2 to x2 is 1, and so on. And then you start to look at basically the distance between x3 and x1, x2 and x1. You can see the 0 in here, and so on. And from here, you can start to take some conclusions. So the first one is we are saying that x1, x2 are the least similar, right? That x1, x2, why? Because we have a 0 value in here, right? Between them in here. x3 and x4 are the most similar. You have 3 and you have 4. Is very close to the 1, it's 0.99. This one is very close behind that one, and this one too. And then you have this like x1 and x3, they are really farther away from each other. x1 and x4, they are farther away from each other. And you can really relate all of that, what you have on the plot in here, right? Which ones are really very close to each other, which ones are not. You can see x1 on the y-axis, x2 in the x-axis, and then that's why the similarity between them is equal to a 0, because they are orthogonal to each other in this case, and so on. But it's very common, and you will do this in the homework number 4, where we create this kind of pairwise similarity. It doesn't matter, we have cosine, we have this similarity, we have distance, but we have a pairwise table that we do in this case. Okay, next is the simple including distance, and as the name entails, basically you just take the difference square and sum like a square root, right? So that's basically the distance between xj and xk in this case. Now is bounded by 0, as basically it means they are in the same location in the Cartesian space, and then it can be very further from each other up to infinity. This should be an open set, not a bracket. This should be a parentheses in here. So there's basically it's far from each other. So when it's 0, that means they are very similar, identical to each other. The larger the number, that means these are less similar to each other in this case. Okay. So it's really the most common used in clustering algorithms because it's very, very simple to use. We can make sense of it on the two-dimensional space, although they are not, we don't really have an orientation element. That's really one of the problems with using including distance, although it's really very highly used in the literature. Same data that we had before. And you can remember what we had before, what x1 and x2, they are really the least similar. x3 and x4 are the most similar when we use cosine similarity. Now, x1 and x4 are dissimilar, and x2 and x3 are the most similar when we use including distance. Right? So now your clustering starts to change based on what kind of measure you are using, as you expect. Right? Again, if you look at this table, now the diagonal in here is zeros. Why? Because we are looking at what distance is, right? The distance between x1 and x1 is 0, right? So remember, this is distance, this is similarity. And I have seen this in the past where students really make this mistake where they think about the table as similarity all the time. This one here is distance, is this similarity, right? Not similarity in this case. Okay, the Manhattan distance, basically, which is really the block distance. Basically, you are really limited by moving from the coordinate based on the axis that you have. So you are moving basically you are moving from this point, you cannot really move diagonally. You have to move either to the right and then up, or you move up and then right to go to the xk, right? And each one of those basically is we are adding them up together, and that basically will give us how far they are from each other. Again, it's bounded by 0 on the lower bound, and that basically means they are maximum similarity, and then we have infinity if they are very far from each other. In this case, it's kind of the L1 norm in here. Again, we can make some conclusion from this pairwise based on, again, this is the similarity is distance. So we have 0 in the diagonal, and here you can see basically we have x1 and x4 are the farthest away from each other using this distance in here. And then what do we have? We have x3 and x2 are closest to each other because we have 2 in this values. Again, Minkowski is another one where this generalization is basically we have the difference to the power r, sum, take the square root, take the rth root in this case. And r is really basically depends on what we are looking at. If r equal to 1, then we have the L1 norm. If r equal to 2, we have the Euclidean distance. And if we have r equal to infinity, that means we have to look at the L infinity norm. And then if r equal to 0, then we are just counting the number of zeros that we have, non-zeros we have, which is the L0 norm in our vector. So this is also another one that we quite a bit use. Usually you have all of these matrices in here or tables, and you start to have a pooling of each one of these. But usually you don't really have that much luxury in the processing because the data is very huge. Okay, we will revisit the Mahalanobis distance later on because we are really looking at the covariance matrix. So what we have, what we have in here notation-wise, we have xj minus xk transpose. If my matrix in here is diagonally with all ones, then what we have is what? Euclidean distance, right? Because we have xj minus xk transpose times xj minus xk. That's will be what? Xj minus xk squared, right? That's basically nothing but the Euclidean distance in this case. But in here we have the covariance matrix is in between, right? And the covariance matrix, just as a refresher for some of you who maybe don't remember it, remember the variance, right? The variance basically we have a summation over I minus the average or the mean value square, and then we sum over all our n samples in this case. And then that will be our variance in this case. The covariance is really a measure of how these two random variables are really related to each other, or how one of them, varying one of them, will change the other, right? So what we have, the difference in here, instead of having xi minus the mean of x, we have xi minus the mean of x times yi minus the y mean value. So we have the two random variables x and y. That will give us basically the covariance in this case. If x and y are identical, then we have basically nothing but this. We have the variance in this case. Now, if I have two random variables, then I will kind of create a covariance matrix where the diagonal in here are the variance for each random variable. So the first one here is the variance for x. This is the variance for y. And here I have the covariance between x and y, the same thing in here. And we can really represent that using some matrices in here. Of course, if we have more than two random variables, then this will be 3 by 3 or 4 by 4 and so on. So this one here, it depends on the dimension of our x, that we have p of them, right? So this one will be p by p matrix in this case, because we have p features for our covariance matrix. Any question about the covariance matrix? Yes.
So if you think covariance of xf, right? That's just the sigma squared.
Yes. Yes. So that's the special case of this, right? Right. This will be xi minus, which will be the same square as this one, right? So just kind of have this in front of you if you ever have this in exam 2, the final exam, because I saw many of you already mix covariance and variance now. Just confusion about them. So this distance in here is using this. Now we are starting to see we are really moving into more complicated ways of how we look at these data points, right? And we are looking at basically the random variable part. So distribution detection, when we have, imagine that you trained your model, and now you are implementing it, and then someone tried to really kind of attack your model by changing the input in a way, right? So now, what the easiest way to start to look at basically is my input data out of distribution or in distribution, right? So now, out of distribution, you look at the your input as a random variable and how far it is from my model, right? So now if you use the Euclidean distance or any of these, is not a very meaningful way to look at this, how far it is from my manifold. But we use the Mahalanobis distance to do that. So this is a very simple case where this is x1. I have 2 features. I have x2 2 features, and I have x3 also 2 features. And then somebody gave me the covariance matrix. We can calculate this in here, take the inverse of it. And now we start to look at the distance between x1 and x2. We have difference transpose. We have the covariance matrix inverse, and then we have the difference between x1 and x2. We put everything together. The distance is 5, right? Distance between x1 and x3, repeat the same thing. Now we have 4. So we're saying basically 1 and 2, right? They are further away from each other compared to 1 and 3, right? So now if you use the Euclidean distance or any of the other block Manhattan distance, for example, then you will, by just looking at it, 1 and 3 will be farther away, more farther away than 1 and 2, right? But now because we really invoke the covariance, basically we look at the distribution of what we are picking our data from, right? It happened that 1 and 3, they are really closer to each other than 1 and 2 in this case, right? And if you look at the visually, right, imagine that we have a visual representation of this. We have some projection using PCA, for example. Then you can see that among the scheme of things, if they belong to the same, cluster, right? And these the ones are far outside. These are out of distribution, or they're really kind of, out of my main cluster. Do you see that? So that's where this example in here, just to give you a hint of, can be the cosine similarity, the L2 norm, L1 norm, all of those that really look at the distance in the feature space. They can be very misleading, right? But once you start to look at the distribution of data using something as simple as the covariance matrix is involved, which is the Mahalanobis distance, and it can be very, very effective, as we'll see later on. We'll study in a paper where we are using this for out of distribution detection. And you can see from here, basically, even if you have your multiple, so this is a 2-dimensional data. Imagine that you have, 50-dimensional data, right? So now you can really project it into a 2-dimensional space using PCA. We'll look at that later on. And then even we have that reduction information, you still see basically Mahalanobis distance can be a very, very good measure because it involves the covariance matrix. It's very simple distance, but it's very, very effective and because of this. Any question about this methodology, this distance? Do you understand what's happening here? Okay. Let's look at the methods. So we will look at the k-means. So we'll have more slides than what I want to emphasize on between now and next week. So k-mean clustering, and you will see later on today, there are, I would say, infinite variations of k-means out there. We'll just focus on the core of it. And then the GMMs, the Gaussian mixture models, because they are very, very powerful models beyond just what we are looking at clustering. So these are the two I will really focus quite a bit. Your homework 4 will be focusing on these 2 methods. Everything else in here, I'm just kind of just making it as FYI in here. Okay, let's look at the k-mean clustering, right? So let's really put things into problem statement, right? So we have the data as before. It's n samples. Each sample has p features, and then as the k-means, this means that we have k clusters. So we have C1 through CK as clusters. Everything else in here is the same, right? So we have the union of the clusters is X. The intersection will be a 0, right? And now we are saying k-means clustering is a centroid-based clustering, right? So we have a centroid. What does it mean? So what we are looking at, this is the pseudocode of what we are looking at. So first of all, you have to pick what k is, right? You have to start, that's the hyperparameter. You have to decide on what is really the number of clusters you have, and can be a pure guess, or it can be based on your side information, right? Once you do that, then the next point is to say, among all of these data, I want to pick the centroid of my 3 clusters. Imagine that I picked k to be equal to 3, for example, and then in here I want to say I want to pick one centroid for each cluster. So I picked, and remember, I'm picking one of the data points, right? So my kind of an implicit condition in k-means the basic algorithm. Any centroid I pick, it has to be part of the data, right? I'm not picking a centroid outside my data, right? Because it's very natural to say, maybe I want to pick something here, 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 but no, it has to be one of the data points, right? So now I picked the red, the green, and the blue as my centroid at this stage. And now the next step is to examine each one of the data points that I don't have as a centroid, how far they are from each of the centroid. So now what you can imagine, I'm looking at this one, I'm calculating the distance between this data point and the red, between this point and the green, and distance between this point and the blue, right? And I say, okay, which one is the minimum distance? It happened to be this one. That means basically this belongs to this cluster, right? I do the same thing for this data point. It happened basically all these points in here, they belong to this cluster, and then all these points in here belong to this cluster. So I have this clustering now. So now I have all of these data points belong to the green cluster, these to the red one, this one to the blue one, and I am distinguishing the centroid as a disk or a circle boundary compared to the square as data points. Okay, and now are we done? That's basically just a one round, right? Because remember, everything in here is based on my guess of my initialization, what the centroids are, right? Now I start to re-examine basically to look at, now I have a new data set in here. I look at the red one and say, between these 2 points, where the centroid is, right? What should be the centroid, right? Now, once I do that, then I'm choosing a new centroid. It happened basically, I'm moving now to this to be the centroid. I look at the green data points. I calculate the centroid among all of them. And then I happen to have another centroid in here that really moved to be away from data points. And then the same thing in here, I did the same thing, right? And now I have a new centroid. I do the calculation again. I keep doing that basically until I get a new classification. And we'll talk about in a minute what is the criteria to stop this one. So initialization will pick a data point that belongs to a centroid belongs to the data point. We don't really pick from outside at this stage. And then we look at the distances. We start to assign clusters to each data point based on the minimum distance between that point and the centroids that I picked in step number 1. And then I reassign centroid again. I recalculate these centroids again. And then finally, I keep doing that until I get to some convergence criteria. Now, the convergence criteria can be a little bit, a little bit more ad hoc than what we like. So there are 3 major convergence criteria. The first one is if I move from one iteration to the next, I don't have any change in my memberships, then I say, okay, I stop here, right? So if each one data point belongs to the same cluster, now I move to the next iteration, nothing changed to each data point, then I end my for loop. Now, the next criteria, maybe the centroid themselves will not change, right? Which is really kind of these two kind of identical, but they're similar, but they are looking at it from a different point of view, right? So if the centroid doesn't really change, they are not really moving, right? Then basically that will end my iterations. And now finally, which is kind of a more common criterion, is I look at the change in the total cost, right? So what is the total cost? It's the sum of the square distance, SSD, right? So this means what? I look at the distances between each of my data points. Remember, I have a summation, the inner summation here over xi that belongs to cj, right? So I'm looking at data points in one cluster, cluster j. I'm looking at distance between each of the points in that cluster and the centroid of that cluster, right? I'm taking the square of that, I'm summing all of them, and then I'm doing that for each one of the clusters, right? That will be my total cost, my total sum of squared distance in here. I will just use the Euclidean distance in this case. So if the cost in here doesn't really change much, so usually it will change a little bit, If it's 0, then definitely we stop. If it changes a little bit, then we have to have an epsilon to say if the change is higher than this much between one iteration and the next, then I will just stop my for loop. If the change is higher, then I keep going, right? So this is the most kind of common method. Is not really as simple as these two methods, but is the most common one. Okay, let's look at this example here in this animation. So we have data on the left-hand side, right? And now we pick on the right-hand side by randomly, we pick these centroid that belong to the data points. So we pick this point to be M1, the centroid for the cluster 1, this one to be the centroid for the cluster 2, and this one is the centroid for the cluster 2, which is this data point here. So I'm using some of these data points as my centroids. And I picked K to be 3 because somebody told me it makes sense. And now what I do next, so what I have on the left-hand side is the same what I have from the right-hand side of the previous page. So now what I do next is really to measure the distance for each data point, look at how far this one from M1, how far this data from M2, how far this from M3. So I have 3 calculations because I have 3 centroids for each data point, and I pick the minimum distance, and I say, okay, this is the centroid. So this one basically with the minimum distance, this belongs to this cluster in here, right? So it happened that I have these data points in here, and this one belong to this cluster. These ones in here belong to this cluster, and these belong to this third cluster, or the M2 cluster in this case. Now, the next step is since I have now new clustering, then I need to calculate a new centroid, right? So this is from the left-hand side, the same as what I have on the right-hand side from the previous page. And now I calculate a new centroid. Now, my centroid moved to be a location where there's no data point, right? So now that's different from the first initialization that I had in the first step, where I picked one of the data points to be my centroids. So now I have a new centroids, and you can imagine now I need to recalculate again the distances. And now I happen to have, so this one, the right-hand side is the same as the left-hand side in here. I look at the distances, and you can see basically this point. In the first iteration, it belonged to M3, but now it belongs to M1, right? So this one, that's the only change between these two steps. I keep now recalculate my centroid again, and you can see basically how M1 moves closer to where the weight of the cluster is, right? Same thing for M2, it moves down here, and M3 basically not much change is happening to it because it's already very close to the heavy weight of the cluster. So, and that's what we are referring to. And these arrows in here, sorry, okay. You see these arrows in here? This is the direction change of the centroid, basically, as we go from one iteration to the next. We don't have one for M2 because the change is very, very small to the left. Okay. So now I do the membership again. And now this one data point, it was belonged to cluster number 1. Now it belongs to cluster number 2. But however, just having this point belong to this cluster M2, you can imagine the impact on M2 will go a little bit further away or north than before. And we keep doing that, right? You can see M2 moved away, right? It was here, and now it moved up here, right? Did we have much change in M1? M1 was here, but you can look at it here, like it was here. The next, oops, it was here and moved, oh, sorry, here. And we keep doing that. So the next step, we do the centroid again calculations. And now it happened that between the 2 iterations next, nothing changed, right? The membership is the same, the centroids will be the same. So I stop my algorithm. That's my clustering in this case, right? And here. Okay, any question about k-mean? Yes. For the k-means, no. For the k-means, even the gmin basically, you have to start with that as a hyperparameter. What usually happens, you will have, start with k equals, a number of k, like 2, 3, 4, 5, right? And then you calculate the total cost, which is this SSD for each one of them, right? As you convert at the end, right? Then you calculate basically the distances, right? And you pick the k with the smallest SSD among all these different algorithms. Okay. So that's one of the problems with clustering is how you pick K. Yes. You mean the initialization of the centroids? Yes. Very good question. And that's actually the slide that we are, this slide. So basically the initialization, right? So there are two things in here. Before I ask that, that's the second half of the slide. So the first one is what Mia is really asking is, what is the K? So now, if this is the ground truth data, right? It's really 3 clusters. If you pick K equal to 3, you get almost perfect results. If you pick K equal to 8, you get this one. So you have too much clustering between them, right? How do you pick which one is better? You just calculate SSD between them, right? Now, the initialization piece is very, very important. Right? If imagine that you have this data, right? If you pick the centroids to be this red in here, I don't know if you can see it, the red star in here and the green star, right? So now the mistake that we did, if usually don't have that visual information, right? But we can tell from here that it's really not a good choice, right? If you do that, then as if you are basically saying you want these are your anchors, right? These 2 stars are your anchors. So all the data has to compare against them, right? So now instead of really clustering based on column wise, you cluster them horizontally, right? So what happened? This becomes one cluster. This becomes one cluster. The next step, this moved to this here. This moved to here, right? But visually, you can imagine. You can look at this. Say, if it were to me, I would say this is one cluster and this is one cluster, right? So I would pick one initialization for one centroid to be on the left-hand side, another one on the right-hand side. If I do that, then I will end up with something like this, right? So now, are they both, correct or wrong, or one is wrong, one is correct? It depends, right? It totally depends, because remember, again, it's very easy to make such conclusions when you have a 2-dimensional or 3-dimensional space, because you can visualize everything. But usually we are dealing with n-dimensional space, right? So we cannot visualize. And even if you use a PCA to collapse your data to a 2-dimensional space, you are losing quite a bit of information and fidelity in your data from the feature space. So the best way is basically kind of, like again, there's an ad hoc, element clustering, and this is one of them. The K is one, and the initialization is the other one. Right? And we'll look at how these compare to GMM next week, the Gaussian mixture models. Okay. So basically, this is kind of answering what the question was about, basically how you choose K. Basically, just a validations point. These are, and I have this FYI in here because I didn't want it to be alarmed that we have to know all these different k-means variations. There are a lot of variations. These are only a subset of variations. And we start to imagine basically kind of, you do subsampling, you do some kind of, collapse of your features. You go many different ways. We will not really go through this. I just want to focus on the very basic idea of k-mean clustering, which is the one I just went through. This one here is just for your information. I will not ask you about this in the exams or the homework. Same thing here, k-means plus plus. I'll just leave this for you to read through. I want to go through. I mentioned this. Yeah, all of this just FYI. Yeah, and here, basically the difference. Yeah, this one was something I think I will ask you in the homework for. Instead of looking at the centroid, we are looking at the geometric median, right? And how that will change. Because for some kind of data, the geometric median, it makes a little bit more sense than having the centroids. And we'll look at this as an example in the homework. That's the only difference between k-medians and k-means, as the name entails. What else? Okay, medians. Yeah, I will leave that for you to read. Yeah, I think that's all what I have. Yeah, I think that's all. Yeah, I'm just leaving these slides for you to just to go through, but I will not really ask about these in the homework on the exams. For the K-mean. But the K-mean itself, the main one is what you have to understand. You will have in the homework at least 2 problems, 3 problems about K-means. Homework number 4. Okay. Okay, so we have the exam on Wednesday. Those who came late, we went through this at the very beginning. Just look at the video. Any question for me? Okay, good luck with the exam. Sorry? Sure. Let me stop the recording. Just